All right, we are going to be going over Unit 2.1. Build some models to hopefully help you things up as you go through these. So question number 1 says, why does MgO have a melting point of 2,800 NaF, which has a melting point of 993 degrees Celsius? So anytime that we are looking at because a metal and a metal and a non-metal. So kind of right off the bat, that's your first hint that we're comparing two ionic compounds. When you see something that has a higher melting point, that means that that compound has the higher lattice energy. So what this is letting me know here is that MgO has stronger bonds and a higher lattice energy. So now I need to think about what is going on with these compounds to give me that particular property that's happening. And so when we talk about Coulomb's law, there are always two arguments that can be had. There is the charge argument, which is the Q1, Q2 portion of Coulomb's law that we pay attention to. And then there's the size argument, which is R squared here. So we need to kind of decide which two things are going to be comparing. Are we going to be comparing two charges, or are we going to be comparing two sizes? And so I always check charge first because I think that's probably the easiest one to deal with. So if we look here and we find Mg is in the second family, which means that it's going to have an oxidation number of +2. Na is going to have an oxidation number of +1. So we can see kind of right away, we have things that are going to be different charges. Typically, we ask questions about things that are close to each other on the periodic table. So the size differences aren't going to be that big of a difference. And O to F is not a huge size difference. So what we're going to be looking at is a charge difference in here. So if we think about MgO and MgO with Coulomb's law, magnesium's charge is a +2, so I usually write that first. And then oxygen's oxidation number, or charge in this case, is going to be a -2. Now, it's going to be divided by, we are not going to put an actual number there, we're just going to put R squared. And the reason we're going to put R squared there is because the size of these two compounds is probably close to being the same because the elements are close to each other and are in the same family. So MgO has a charge on top of a +4, and NaF has a charge of a +1 for sodium times a -1 for fluorine, and approximately the same size for the two molecules. So when we compare these two, it's definitely a charge difference because the size is approximately the same. So when we start talking about explaining the properties, we are going to be talking about the different charges. So what I am going to want to say is that MgO has a higher melting point than NaF because its ions are more strongly attracted to each other than those in NaF. Oop. Okay, now that is kind of our thesis statement there. That's us answering the question. That's always the first thing that you have to do. Now, the College Board really likes it when we talk about Coulomb's law in our problems. So I'm going to say, according to Coulomb's law, since Mg has a +2 charge and Na has a +1 charge, I'm going to put that in parentheses just because it's kind of hard to see. The compound formed with Mg will have stronger attractions. leading to a higher melting point. I'm just going to put MP for melting point there. Now, I personally, when I'm talking about Coulomb's law charges, always really like to put these calculations in the top two. So if we are comparing two things that have similar sizes but different charges, the stronger attraction is going to be to the larger ion. Now, I'm going to take these out for a second. I built some lattices for you. So this is, let's say, two different lattices here for sodium fluoride and for magnesium oxide. So what you have to think about is we have two different ions that are approximately the same size. So if we have, let's say this is sodium fluoride here, and this is magnesium oxide. They have approximately the same ions in their lattices. So I'm just kind of showing you how I built this. These are mini marshmallows, by the way, and these are dots. But what I did was I worked and got these together, and you can kind of see here that this is a pretty loose little lattice here, and this is a pretty firm lattice, and it's because these dots are stickier. So what you can kind of imagine happens with Coulomb's law is that if I have a greater charge, there's a greater magnetic attraction between the ions. These are actually more strongly attracted to each other, and so they're kind of quote unquote stickier. So they actually stick to each other better because they have a stronger charge, okay? Whereas this is just +1 and +1. This is a +2 and a -2, and so we get a much more sturdy lattice when we have these two together, okay? So that is our first example. Our second question asks us, I'll fold this up here. Our second question asks, which compound, NaCl or NaI, would have the higher lattice energy, and explain. Okay, so we're comparing two things now that have identical elements in them except for the anion, and we are going to have to figure out which has the lattice energy. So again, we're always going to look in these situations with a combination of charge and size. So again, I always really like to write down the Q1, Q2 over R squared. And this is one of those equations that may not be printed on your equation sheet, but I always recommend writing it on there so that you don't forget it. So if we compare NaCl and NaI, okay, NaCl has a charge of +1 and -1 on the numerator. NaI has also a +1 and a -1. So if we are doing a charge comparison, this is not a useful argument anymore. However, we need to take a look at the size, okay? So if I compare chlorine and iodine here, Cl has a smaller radius than iodine does. So when I compare my two compounds, they both have Na in them. And the Na is the same size. Let's assume if I can actually draw it correctly. But the Cl is smaller in size than the I is. The I is larger because it has the extra electron shells. So in this situation, the distance from the center to the center is going to be larger for NaI than it is for NaCl. And so what happens is I have for NaCl a smaller number on the bottom. And I know that's not very, maybe let's say math friendly, but we're not asking you to do any actual math. We're asking you to kind of think it out. And this bottom number here is going to be a larger number, and both of these are going to be squared. So if you think about the math, and let's pretend to put a number in here. We both have the same number on top, but let's say this is a number. If I have 1 divided by 2 squared, that's 1 over 4, okay? If I have 1 over, let's say, 8 squared, that's 1 over 64. What happens is when we talk about the attractive forces, or what they also call them electrostatic forces, we have these charges here. This is a stronger attraction for NaCl than it is for NaI, and it's because the two nuclei can't get close to each other. So what we'll talk about is their size and how the two nuclei being further apart aren't as attracted to each other. So back to the question, it says which compound would have the higher lattice energy, and explain. So what we're going to do is I would say I would expect NaCl to have a higher lattice energy than NaI. Okay, so the first thing we do is we answered the question. That's worth 1 point, and then the explanation point always gives us the second one. So I would again go, according to Coulomb's law, they love to see that in there, but you have to use it correctly. Atoms that are closer together have a stronger attraction than atoms that are further apart. Okay, so that's us talking that we know what Coulomb's law means, but that is not enough to answer this because we have to talk about Cl. So what I would say is, because Cl has fewer electron shells, it forms a shorter bond with Na, making it more strongly attracted to Na than I would be. This increases the lattice energy for NaCl. Okay, so when I think about answering these questions, I actually A, answer the question, but then B, talk about the concept and how I support that. Now, I did build some more models for you because we all love some models. So imagine that this here is NaF. This is regular big old marshmallows. And this is NaCl. So when we think about the stability of a lattice, the ability for, and again, maybe this isn't perfectly to scale, but think about the size here. When I have smaller atoms, they are able to bond better because their two nuclei can get closer together. And again, this is not maybe perfect because these toothpicks are a little bit the same size. But if we actually look at the physical stability that I have here, it's a pretty sturdy little structure for NaCl. I don't know if you can see this, but my structure is pretty wobbly here for the NaI, and that is because it has these big kind of poofy marshmallows. And if you think about an atom not maybe being big and poofy, but being large, if my two nuclei can't get close to each other in an ionic bond, it's going to not give me as strong of a lattice structure. So this is much more kind of floppy, I guess the best way. It doesn't hold its shape. It's getting really janky and broken looking. You'll kind of see it melting on the screen here. Whereas this, I can move it around and it still kind of retains its shape. And if we think about lattices in terms of ions that are formed, the little ions in terms of their physical size can get closer to each other, and they're more strongly attracted than these big beefy guys here. So hopefully that clears things up. If you have any questions, pop into a Google Meet and we will get things figured out. Good luck!